Hey there, chemist. Dr. O'Malley here, and I just want to run through some things about the final project for this semester. This is a synthesis project that involves visiting this website. This is from the University of Wisconsin's chemistry department. It's a fantastic archive of all sorts of total syntheses that have been done, and the idea is for you to pick a molecule that's been synthesized and try to navigate the synthesis and see if you can translate some of the reactions. Not all of them, but let's say at least 5 of the transformations that you see. So I'm going to do one right now. This is the molecule called fumagillol. This synthesis was published in 2001, and I'm going to pick some of these steps. I'll start from the beginning and walk through what I think are the mechanisms for those transformations, trying to apply some of the things that we've learned this semester, but also maybe learning a couple of new reactions along the way. And that's really the goal of this project, for you to maybe even learn a few new things that are very related to what we've done, whether it's a direct application or not. It hopefully will be a useful experience for you. Before I even go too far into this, I want to point out something that I discovered just as I was doing this. It looked to me like there was an inversion of stereochemistry at a particular step where nothing actually happened at the carbon in question. So here we have this dashed line going to what's called a PMB protecting group, and here it is just completely inverted. And I started working on this mechanism and thinking, was there anything that could change the stereochemistry at that carbon separate from the reaction that happens here? Well, I actually stopped working on that and just went and checked the source. At the bottom of the synthesis on the website where you can get this from the University of Wisconsin is a link to the journal, and it takes you to a page that looks like this, which is an ACS, American Chemical Society publication. This is called Organic Letters. And even though I can't access the article itself, everybody in the public has access to what's called supporting information. So when I clicked that link right there that says supporting info, I was able to look at a PDF and find this particular molecule. And this is how they drew the molecule that's labeled A up here. This was transcribed by some students at Wisconsin, and I'm trying to see if they have the right stereochemistry or not. And it looks like they just accidentally goofed. The literature reports it as an R asymmetric center, and I can just check my rules of rotation, and indeed that is an R asymmetric carbon. They accidentally drew it as an S. So in a couple of the steps, I'm changing that stereochemistry because I want to show what actually was happened. So let's go into the 5 mechanisms I chose. The first step is this transformation here is just a cropped picture of what's on the synthesis. This is a reagent that I've not seen before. It's a selenium anion, a selenide, followed by a reagent I have seen. That's diazomethane, which makes the methyl ester. That's why I chose to start with this step, because I recognize that diazomethane step. It means I had to figure out how this selenium thing works. There's the corrected product, by the way, just to change in the stereochemistry. That means the starting material is actually the other enantiomer as well. So I'm going to start with that. So here is this alpha hydroxylactone. The sodium is a spectator ion, so that's a selenium anion, and that actually is attacking this carbon right here. Whoops, I'm already missing an arrow, aren't I? There should be an arrow from selenium to the carbon, obviously. Then there's nothing written in this scheme, but there must be a source of proton where this oxygen anion picks up an H to become a carboxylic acid. That must be the case because diazomethane reacts with carboxylic acids. So this might be something you encounter when you look at mechanisms too. Maybe there's a workup procedure, just like this one, that they didn't actually write on top of the reaction sequence. That doesn't mean it didn't happen. Use the information you know from the reactions you learned this semester and write down what makes sense. This is not changing the synthesis, it's applying something we know. Anyway, the carboxylic acid reacts with diazomethane. That's a nucleophilic carbon, that's a basic carbon. It takes the H away, you get a carboxylate. That reacts with this methyl diazonium, kicks out a nitrogen leaving group, and that's how you get your methyl ester. 1 down, 4 to go. The next one I chose is actually right after it. It takes this methyl ester we just made, let me correct the stereochemistry, there we go, and it puts on what's called a PMB protecting group. Let me fix that stereochemistry, there we go. I also notice I reduce the ester down to an aldehyde, so I have 2 things I have to do back to back. I do not recognize this reagent or CSA, but a quick internet search taught me what those things look like, and CSA is just a source of acid. So here's what that reagent actually looks like. I'm actually going to abbreviate some of the PMB group. It's just an R, and you can do that too when you're writing these out. If you want to abbreviate parts of molecules or reagents where nothing actually changes, go ahead and abbreviate them. That's okay. It saves space and it shows that you're focusing on the transformations that really happen. The alcohol attacks this carbon attached to this imidate leaving group. it kicks that leaving group out, and I get essentially a protonated version of the product, or of the intermediate. I lose an H+, any conjugate base can come along and take that away. That is such a well-known transformation for everyone in this course. I'm not even drawing the arrows for that. You know how that happens. After that, though, we have dibal. Remember, dibal, diisobutyl aluminum hydride, is a source of H-, so it attacks the methyl ester, just like any nucleophilic addition reaction. I reform the carbonyl and kick out methoxide. That's how you get the aldehyde. 2 down, 3 to go. The third one is an aldol addition, a recent reaction, and here's where I noticed that stereochemical change. So this is the last time I have to update the structure. This is a big amide derivative on the left that's LDA, lithium disopropylamide, and an aldehyde. So I'm going to make an enolate on this alpha carbon and attack that aldehyde. There's a lot of stereochemical consequences, but my job for this is just to show how the bonds form. So here's LDA forming an enolate on the alpha carbon of this starting material. That enolate attacks the aldehyde. This is our most recent unit, where I form this new carbon-carbon bond between the now alpha and beta carbon. Again, there's no proton source written right here, but there must be some type of proton workup procedure to give me the alcohol. And I'm putting the stereochemistry that I know I get from the literature. I'm not even trying to rationalize it in this, but you certainly can. If you come across a reaction where the stereochemical features seem to be significant enough that you want to tackle how they happen, by all means, try to come up with where the stereochemistry comes from in your reactions. I think that's a useful exercise. The fourth one, now we've got the molecule we just made, essentially. It's written right to left in this box, so look out for that. Look for the direction of the arrow in case you're confused about how it goes from one to the other. Sometimes it snakes around in a zigzag. I take this thing, which is called a Weinreb amide, and it gets converted to a ketone. Prior to that, I protect this alcohol as a silyl ether, so we show that. Here's the alcohol attacking, this is TMS chloride, trimethylsilyl chloride. We've seen TBS chloride, this is the same type of reagent. Silicon is a much bigger atom, so it can do an SN2 like we're seeing here. I get a protonated silyl ether, that must be what triethylamine is for. It will take away that extra H. And then I have a Grignard addition to this special type of amide. So the carbon attached to the magnesium is the nucleophilic carbon. It hits the carbonyl carbon. I reform the carbon-oxygen double bond, and I must kick out this nitrogen leaving group, and that explains the product. Last one that I chose to analyze here is a metathesis reaction. There's Grubbs' catalyst being used to do a ring-closing metathesis. That's what RCM stands for. And it brings together 2 alkenes and stitches them to make this 6-membered ring. Again, we're going right to left here. So if I redraw that starting material, I'm abbreviating the catalyst. You can do this too if you do a metathesis reaction, or a number of others if there's simplified versions of it that you want to draw. This is how we learned the metathesis reaction back in Orgo 1. You do a cycloaddition to give this 4-membered ruthenium-containing intermediate, and then that actually delivers the catalyst into the molecule itself. And that's what reacts. I'm just going to redraw it in this conformation. That's what reacts, does another 2+2 cycloaddition with the alkene up there. It gives you a new 4-membered ring, which collapses to give you your product. I didn't draw it, but actually regenerates the ruthenium catalyst in the end. So those are the 5 transformations that I chose to do for this fumagillol synthesis. Hopefully you recognized some from this course and learned a few along the way. Thanks for watching.